welcome to the class of intelligent product design. And after the concepts, the materials, the structures, the mechanisms, sensors and actuators, the most important thing now we need is to give some kind of a power of control, so that the system can change according to the change in the environment or according to the change of need. So, that is why today we will initiate our discussions on the introduction to the control system. So, we will talk about the control systems that we will need, which is a very important part of this intelligent product design journey. Now, before we actually talk about this, you can see that the application of the control theorem is really very vast. You think of unmanned aerial vehicle, say UAV for defense. You think of a network, you think of microfluidic channel in a MEMS device, or you think of any mathematical problem. Everywhere there are certain challenges which can be addressed with the help of control system. So, the theory of control system is very generic. We will try to touch only those part of it which are absolutely required for us in order to develop a control system for our sensors, actuators and the plant. If I look into the journey of these, that how these control systems are getting embedded more and more in a product, I think we can consider robotics as one of the best example of it, and the tools that also are getting digitally controlled. Now, one hand we have a flexibility in our mind always in any manufacturing system, how to impart more and more flexibility. That means how to use first of all a versatile tool which can be used, let us say, for turning, for grinding, many purposes, and then how to make it high precision also with the help of some master slave manipulation. Then create a programmable CNC system, so that you can have different type of operations through the same system, and then the digital control system. And as we increase more and more this flexibility direction, more flexibility, gradually we will come to a situation where the system can be integrated with vision, with man-machine interface, supervisory control. Each one of them will increase the flexibility of the system immensely. On the other hand, if you look at the autonomous systems, that means when the system can take its decision on its own, then starting from hand tool we go to the power tools, and then from the power tools we come to again MC machines and robotics. Here we can also see that some of the systems from the power tools which has a high automation level can actually be remodeled in terms of making a robotic solution. And then if I further try to increase the autonomy or flexibility, it will land us to this part, and here we are going to get finally the intelligent systems which are highly flexible and highly autonomous. Okay? So, that is the thing that we are trying to achieve, and in order to achieve that we have to understand certain basics of the control theory. That is what brings us to the picture of today's lecture. So, here I have shown a simple closed loop control of a plant. What we have in this picture in the left hand side? I have a reference. Okay. So, what does the reference means? Reference means a desire to go towards a particular direction, okay, or a particular type of, let us say temperature, pressure, displacement, force, anything that you want to achieve through a system. Okay. So, for a cutting tool, it can be something like a particular type of a force signal you would like to achieve. For a vibration, it can be something like a particular type of a displacement that you would like to achieve. For a car, automated car, it can be like you have a trajectory given that this trajectory is to be followed, and currently let us say the car heading is in this direction. So, that means my reference is this way and I am heading this way. So, I need to modify myself so that I can turn myself towards the actual trajectory that I am supposed to follow. So, that is what is the reference, that these desired trajectory, desired line, desired shape, this is reference. Now, often we employ an input filter. Why do we employ input filter? Because the trajectory that we create many times may have some disturbance in it. It may not be very much clear, like a clear curve, a clear line. Now, this disturbances the system did not follow. So, it needs to filter out the disturbances and create a clear goal in front of the system. Then we take a break from rest and we come to this part, which is the process, or in our case we can write it as plant or we can write it as product, whatever way we want, but the idea is the same, that there is a product and this product in its interaction with the environment is showing certain outputs. These outputs I am measuring through sensor or sensors, and then that data, the output data through the sensor here is coming back and feed it at this point. And you also have a desired trajectory with you. So, for example, in this case, as I told you, that in a particular point you know that you have to go tangential to this line, this should be the point, and the sensor tells you that you are heading this way. So, that means the difference between, say suppose with respect to a standard x axis, the difference between this angle which is theta desired versus this angle which is theta sensed. So, theta d minus theta s is what is going to drive the system. So, you have this theta desired here and you have the theta s here. The difference between the two is going to drive the system. And we have a controller here, which is what we learn how to have this controller. In some cases we can keep a simple gain here, k, constant gain. So, k and then theta d minus theta s difference is going to drive an actuator. That actuator in the case of a car can be simply an engine that is to be driven. In the case of many other systems, it can be something else. It can be like a motor control, or it can be like a hydraulic system control, whatever actuators we have learned earlier, an electromagnetic system or a smart actuator. So, that needs to be driven with the help of the control signal, and because of these additional inputs, there will be changes in the process. There will be some disturbances that can also get fixed while in that process, and we measure the output and continuously rectify the process. This is the idea of closed loop control of a plant or a product. Now, let us also think of it that simultaneously this entire thing is to be done in a domain which is to be mathematical in nature. Okay. So, we never directly put a controller and see the performance, because that can be catastrophic. Suppose you have to launch an aircraft and you do not try any new controller in it directly. You have to do it on a model first, you have to satisfy yourself on the performance, then only you can extend the idea. So, modeling is equally important in order to do that simultaneously, and by modeling I mean a mathematical representation of the system dynamics. And these models, please remember that they are never exact, but they can be predictive models that can be used in ways that the system can perform certain types of analysis like parametric variations, and can easily be done on the actual system. So, that is the requirement of the model, but model can be simplified to the extent that it can do a particular type of a behavior can be modeled, and models then can run much more quickly than the actual system. So, you need to keep in mind that a single system may have actually many models possible. Now, how do I model a system? A system may be modeled by either defining the input output characteristics or through something which is called a set of state variables. So, input output characteristics are related to that the input is the external excitation of the system, which is extrinsic to the system, and then outputs are the variables that are calculated or measured by the system. And hence a relationship can come out like this, okay, where u is the input. So, here u is the input and y is the output. Now, many a times simply y and u will not be connected. That is possibly the simplest linear system, where I can write that a0 y equals to b0 ut. In other words, y is simply b0 over a0 ut, or some kind of a constant c0 ut. So, this is the simplest one. Many a times the output can depend on not only the input, but rate of change of inputs. That is what u1 and u2 to um talks about. And similarly, instead of only y, you can have y dot, double differentiation of y up to nth. That is a very generic relationship of input and output of a system. Now, one thing you have to keep in your mind, that choice of inputs and outputs depends on the point of view. You have complete freedom to do that. So, input is what factors are external to the model, you have to keep in your mind, and output is what physical variables you are actually trying to measure. When we will go for state space, we will not actually look into the output directly, but we will look into that what are the exact parameters required in order to describe the dynamics of the system, particularly such that it has to be a minimum set of parameters in order to describe all the energies involved in the system. I will come to that in a minute. Now, let us look at this car. Okay. It is a car that is supposed to be intelligent, autonomous, and I want to model the cruise control part of it, like the trajectory control and what should be the speed, etc. So, what could be the equation of motion of such a car? What could be the transfer function? These are the type of things that we will look into how to do. Another example could be that there is a disc that is getting read. Okay. So, there is a stylus, and as this disc is rotating at a high speed, this stylus at different points it is actually reading this entire system, and then from that it is taking some output of it, that is a combination of streams of 1 and zeros that gives us some values. And thus this, as it is rotating this entire part at different parts, it can be representation of a memory drive, it can read different values, etc. Again, here the input can be that what is the moment that I am giving here in order to rotate, and what is the output theta 2. Now, let us actually look into our first problem. In the first problem, let us say I have a system to measure the velocity of the car. Okay. Then what is going to be the sort of governing equation of the system? Well, first thing is that the car is moving in a particular direction, so it must be having an inertia force. So, mu dot is actually representative of the inertia force. The second thing is that as the car is trying to move, there will be some resistance from air on the car, and that can be proportional to the velocity of the car. So, this is the velocity. this is the velocity of the car. So, that proportionality constant is also called damping constant. So, that is plus du. So, if you try to actually sort of draw the free body diagram of the system, there is a force that is driving the car. Of course, it is coming from the engine, and as it is trying to move this way, there is an inertia force which is mu dot, and there is a damping which is du. So, that means the equation of equilibrium is mu dot plus du must be equal to the force that is applied, and that is how we get the governing equation of motion of the system, EOM. In this problem, it is not translation, it is rotation. So, in this case, however, it is not just one body also, there are two bodies here, one body here and this other system here. So, in this case, there are two rotations, one rotation is taking place at the disk level here, that is this theta 1 rotation, and another is happening here. So, you have basically any one of these equations, if you take I1 theta 1 double dot, which is the inertia force corresponding to this disk, then C theta 1 dot minus theta 2 dot, which is the energy that is dissipated due to damping. One additional thing would come here, if you consider this shaft to be flexible, then K theta 1 minus theta 2, that is the energy related to the, or the force related to the flexibility. So, this is, in this equation we can say that the first is the inertia force, the second term is the damping, and the third term is what you call the spring force, resistive force from spring. And for equilibrium, all these three things together should be 0, either or else in the other case, for example, that there is a moment that is applied on the system. So, this is the way we can represent such a system. Now, this is a kind of a input output relationship, and then you can transfer this relationship in terms of the Laplacian domain. Okay? We do it many times because that would become then much easier for us in terms of representing the transfer function, representing the system as a set of algebraic equation. Like I will show you that in the first case, if you remember, we had mu dot plus some du, let us say in this case we write it as bu equals to f. Okay. Now, if I apply a Laplacian transformation to this equation, then it would become Sm capital U S plus B U S equals to f bar S. This is Laplace transformed. So, then I can write after this a simple algebraic manipulation to write it like this, and that means U S over f bar S will be equal to 1 over Sm plus B. And similarly, in the second system I can write it as this. Now, keep in mind that in this case the system is first order, and in this case the system is second order. Now, on the state space modeling, because that is another way of representing the system, we have to keep in mind that this is, as I told you, a set of independent physical quantities, the specification of which, the absence of excitation, completely determines the future evolution of the system. Okay. So, independent physical quantity is something that is also I referred as minimum number of parameters that are required. Now, let us look into this further, that how do we determine what are the minimum numbers, and that for that matter we have to keep track of that what are the different energies involved in the system. Okay. So, for example, when a ball is falling down, so a ball is falling down, so what are the different energies that will be involved in it? Of course, the kinetic energy of the ball. So, if this ball is of mass m, then it must be something like half m v square, and let us say I define it with respect to the height h, then you can write it as half m h dot square. and then also what is the potential energy. So, this is the kinetic energy, potential energy is mgh, right. So, if these are the two things that are required, then definitely you must have two states here, H and H dot, in order to define all the energies involved in the system. That is what we have told here. Now, then the state space modeling also through this tracking will actually give us a governing equation of motion, just like we have obtained in the other case. The only the point here is that for state space representation, we will be happy to keep the relationship in time domain, whereas in the other case we represent it generally in the frequency domain. Now, once I get this equation of motion, I know that what are my states, like in this case two states are required. So, I can choose between position and velocity, or position and acceleration, or velocity and acceleration, any two. That is my minimum set. State space beauty is that it need not be unique, but the number is constant in each and every case. So, like in this case, if I consider x and x dot as the two state vectors, then I can write down that earlier equation in terms of a first order state variation. Okay. So, you can just try it yourself, it is very simple, something like you see mx double dot plus cx dot plus kx equals to ft. That was what we had, let us say, okay, or small ft or small ft. Then I can write it here as, so I can write each one of them as small m, small c and small k. Then I can write here x double dot plus c by m x dot plus k by m x equals to f by m, ft by m. And then I am writing these two states. So, very simply I can write it as this is my first state x1, this is my second state x2. So, x1 is x and x2 is x dot. So, now I can write the first kind of a what you call the identity is that x1 dot, which is x dot, equals to x2. This is the first identity we can simply see, and you see everything is to be in first order. Then I can write the second equation in terms of the states here. So, what will be x double dot? X double dot will be x2 dot. We already know c by m x dot is x2 simply, and k by m x1 equals to f over m. I am just keeping the t out because it is implicit, there is a time there. So, now we have two state equations. I can write it down nicely as x1 dot equals to 0 x1 plus 1 x2, and the second equation as x2 dot equals to minus k by m x1 minus c by m x2 plus f over m. And you see, then this is the part which is coming here, and in the matrix I get this 0 1 minus k by m minus c by m, and then I have the additional part, that is the input part, that is 0 1 f m. That gives us a standard structure which is also called x dot equals to ax plus bu, where A is defined as this matrix, that is A, and this is B. Okay. So, we can get a standard representation of the system. Now, the output of a state space system can now be defined in terms of the states. So, it can be something as simple as yt equals to some constant times the states, but if the input disturbance is also affecting, then I can have some extra term like dut into it, but in general d is 0. Now, if I get this type of equation, that is x dot equals to ax plus bu and y equals to cx plus du, your natural question will be that how do I solve it? That means, how do I get x? Okay. So, this I can get just like the integration factor that you have done for first order equations. Only thing here, it is a matrix equation. So, you get xt as e to the power at x0 and the additional part as 0 to t integration of e to the power at minus tau bu tau d tau. Okay. So, this should be bu tau d tau, bu tau d tau. and remember that e to the power at is a matrix, okay, where I is an identity matrix. So, I is an identity matrix. Okay. And once I get this, I can also of course write this equation in the Laplace transformation domain also. I can write it as x s equals to s I minus a inverse p u s, and that way I get a Laplacian transformation and the corresponding transfer function of the system. Now, you check yourself whether you can do this problem, like let us say I have two bodies, two masses interconnected by some springs and spring and dashpot, and some force is working on it. Can we find out that what will be the state space representation of the system? Try it with this pulley system also and check whether you can do it. For that autonomous car, I can go further, like I can put some mass here and then some mass for the seat, and then the seat damping, seat spring, then the tires and the front spring, front absorber, front tire, rear spring, rear absorber, rear tires. So, then I get a complete model of the systems. Sometimes, as I told you, models need not be unique, models can be simplified also. Sometimes I can simply make something which we call, say in this case, what is the simplification? Like an automobile is having 4 wheels, but I have reduced it to 2 wheels. That means, I have considered that even though there are 4 wheels there, so from the top view you can see there are 4 wheels there, but I can keep a set of this and I can keep a set of this, so that ultimately it becomes an equivalent 2 wheel system. Further, I can integrate this also and I can get it as a single wheel equivalent system. We will call this as a quarter car model. So, this is the most simplified model of the system. Now, while doing this, you may come across the nonlinearities, and that is something like the stiffness is nonlinear. So, which means at different values it is going to have different stiffnesses. So, you can accordingly consider the nonlinearity in the system. Now, here are some very common test waveforms, like if it is a impulse signal, then how this input will look like, it is a Dirac delta function. If it is step, it is something like this. If it is ramp, this is it. If it is parabola, it looks like this, half of t square, and for sinusoidal, of course, it is a sinusoidal signal. So, for any mechanical system that you are trying to find out the response of the system, instead of trying for arbitrary inputs or excitation, we generally try to model it against one of these, like impulse, step, ramp, parabola or sinusoid. So, you need to keep these inputs always in your mind. Now, whatever I have done for the mechanical system can also be done for the electrical system by following the Kirchhoff's current law and Kirchhoff's voltage law. That is, the algebraic sum of currents leaving a junction or node equals the algebraic sum of currents entering the node or the junction, and voltage law, which states that the algebraic sum of all voltages taken around a closed path in a circuit is 0. So, we can adopt this for a LRC circuit, an inductor, a resistor and a capacitor, and there is a voltage in it, and we can also create their impedances, their sort of representation in the Laplace transformation domain, and we can get the equation of motion of the system. Something similar we can do not only for one loop, but also for a 2 loop system we can try, and you can see that this is the transfer function that will come out of it. It will be a good idea to practice such a system. And suppose I now know that how to describe a system. So, if I go for modeling of a DC servo motor, then what would it involve? Well, here also it would involve a resistor, it would involve an inductor, and there will be the mechanical system which is getting rotated, and of course, there is a current, the field current that will be produced by the electromagnetic system. So, in the next lecture, I am going to talk about that how to model this DC servo motor. Thank you.